Hey guys, what's up? Mr. Custis here. Uh, Turns out my daughter threw up a couple times after school yesterday, so I'm not there today. So I'm gonna go through this scatter plots packet that we have. Make sure you guys know exactly what's going on in it. I'm even gonna start back with what we did last class, just to make sure if you were absent or sleeping, you still know what was going on. All right. So scatter plots. Um, First of all, gives you a visual idea of what is happening with your data. All right, it's a way to estimate our data and what's happening. So we're going to make some scatter plots here at the beginning. Go through that. Obviously, it's a video. Feel free to pause it at any point. Stop and go back. Anything you miss. Um, so our first scatter plot here was the height and weight of four eighth grade boys. So we graphed this. We scaled our x-axis here with the feet. And we can see the feet here was all between 5 and 6 feet. So we started at 5 feet, went to 6 feet. And each line here was a tenth. We skipped some lines just because we didn't have space to write down the label for each individual line. But each line was a tenth. So 5, 5.1, 5.2, 5.3, and so on here. And then the weight, really we started at 130 here and had to get up to 200. So we skipped some here at the beginning, right? We didn't go from like 0 to 120. We skipped all those numbers and then went up to 200 there. So we had those 4 points. All right, and then this line, we call it the line of best fit. We'll have that the notes over here in just a second over to the right. But this line of best fit is our average. It's kind of our estimate for any height, any weight that we're interested in here. So if you said you're 170 pounds, eighth grade boy, I would estimate that you are 5.7, 5.8 inches tall. So that'd be like 5'9" ish, 5'10". So um, that's kind of the whole deal. Why we might actually use a scatter plot. If someone said they're 6 feet tall, I would estimate they'd be between 190 200 pounds, probably a little closer to maybe like 193, 194. That'd be just be an estimate. Right, it's not exact. It's just an estimated guess based on the 4 students who we have data for here. All right. We have another scatter plot that we did over here. This one is time spent studying or minutes studied, and then their grade on the test. All right, so we plotted all 10 of these points. We kind of made this elongated oval around most of the points. We had a couple of points that were not bunched up. They weren't clustered up with our other points. We called those outliers, right? The points who are kind of far away there, calling those outliers. They're not close to our other points there, right? So we can use this, all right? We see this as another positive, another increasing graph. So that's going to come up here in just a second. We're going to have some notes on that down here at the bottom. And we could use this line here to estimate our test score based on the minutes we study. Or we can, if we want to know, what grade we want, if you know what grade you want, then we can estimate how many minutes you need to study to get that grade, right? And just let's do an example. If you want to get an 80%, right, a B, here's the 80%, here's the B, right here. You'd have to study for almost 80 minutes to get a B based on the 10 students there that we sampled, that we have data for, all right? So we did a little bit of vocab down here at the bottom. Outlier is the point that is closest to the others. Our line of best fit, right? That line that we draw kind of in the middle of all those points. It's the estimate of the points. Again, it's not connect the dots, right? We didn't connect all those dots. We just drew a line down the middle of all those points. And then we have an increasing graph here, right? That's a positive relationship. Another word we can use for that is correlation, right? So positive relationship or correlation. Those words mean the same thing. And when we have a positive relationship or a positive correlation, that means as one variable increases, the other variable also increases. All right, so that was our first page. Coming over to the next page, we learn a little more about correlation, a little more about relationship, and we start using the word strong or weak. All right, so sometimes here in the paper, it'll say high or low, but a strong correlation is the same as a weak correlation. Strong and weak. Whoops, that was dumb. Strong doesn't mean weak. Strong is the same as high here. And then weak is the same as low. All right. Don't confuse these with positive and negative. Those mean something different. All right, but when our points are all bunched up, this one's actually perfect because it's like a perfect line. These are still a little bit scattered. So this is a high or a strong positive correlation. You can also have a strong or high negative correlation, right? Strong doesn't only go with positive or only go with negative. It can go with either one. That's just telling us how closely bunched up or clustered up those points are. All right. We also have a low positive correlation here. The points are a little more scattered out, so we can call that low or a weak positive correlation. Here we have no correlation where the points are just kind of scattered all over the place. Here we have a low negative correlation. Right, the points are scattered around, but they are still decreasing. Right, as we go to the right, they are decreasing. Here's a high negative correlation. The points are a little more bunched up, but they're also decreasing. Right, as we go to the right, they're decreasing. And then we have a perfect negative correlation where, this is pretty much a perfect line here, and it's decreasing, right? It's going down. All right, so then the next thing I asked you guys to do was 1 through 4 down here at the bottom. I asked you all to go ahead and try those on your own, determine if it was positive or negative, strong or weak. And we talked about these in class last time. So this one was a strong positive correlation. This was a strong negative correlation. All right, these points are all pretty bunched up. These are increasing as we go to the right. These are decreasing as we go to the right. This we said weak negative. If you said there's no correlation here, that'd be fine too. They're kind of decreasing. You can kind of draw, but this is pretty weak, right? Those are pretty spread out. If you said there's no correlation, I wouldn't disagree with you on that either. It's really kind of up for interpretation on that one. And then we had just some example word problems here. So a number of hours studying and test scores, right? So we would expect as the number of hours you study increases, your test score should also increase. So that's positive, and it's probably pretty strong, right? Probably pretty strong. The water bill in the winter, you could have said positive, you could have said negative, you could have said no correlation. Honestly, it just depends on your justification, all right? If you said the water bill is higher in the winter because I like to go home and take a hot shower every night because I'm cold, all right? So you said it's positive for that reason, I'd take it. Yeah, that would work. If you said it's lower because maybe you use a lot more water in the summer because you're outside playing in the sprinkler with the hose, you're watering flowers, you're filling up your pool, whatever, right? Those would be reasons maybe you'd use more water when it's hot out. So that would make it negative, right? Because you'd be using less water in the winter. Your water usage would go down, would decrease as the winter went up or increased, right? You could also say it's no correlation if you're saying you use the same amount of water every month, right? Your water bill never changes. You always use the same amount of water, no matter if it's summer, fall, winter, spring. Then we'd say it's no correlation. All right. This last one I think was pretty straightforward. We said annual salary and shoe size. We said no correlation. I don't think how big your foot is really has anything to do with how much money you make, right? Annual salary means how much money you make a year, and I don't think those two things are really related. If I was to perhaps get data points from like NBA players, maybe it's correlated, right? Maybe the bigger the NBA player's foot is, the more money they make, right? Typically, the taller the player, the more money they're going to make. That's not always true, right? There's obviously some shorter players that make, like Steph Curry, not nearly as tall, like 6'3", makes a ton of money. And you have some 7-foot guys that don't make a lot of money because they're not as skilled. But for the most part, the taller you are, the more money you're going to make. Two people who are the, you know, same skills, right? Same shooting ability, same athleticism, all that. The taller player is going to be better, right? So they're going to make more money. So for the most part, right, I would say no correlation between annual salary and shoe size. But if we did like in a specific example and you said that, if you said that was positive, right, as salary increases, shoe size increases because the taller you are, the more money you're going to make at basketball. Okay, yeah, I would give you credit for that. That would make sense. All right. Next thing I asked you to do was 1 through 6 over here on the top of the next page. And this is a little more straightforward. That's no correlation. Those points are just spread out. This is a negative correlation, and I would say that's pretty weak. They're pretty spread out here, but it is decreasing, so it's negative. This again is pretty weak, but it is positive. Those are increasing. This is positive, much stronger correlation. Those points are all much closer to our line. This is a negative, again, stronger correlation. Those points are all pretty clustered up, much closer to our line. And then 6 there is no correlation, all right? No correlation there on 6, all right? 7, history, test, and how much time they slept the night before the test. So we plotted all these points, drew our line of best fit, and just talked about it, all right? So if you wanted to get a C, right? If you just, I just need a C. Well, you better get at least, looks like about 5.5, almost 6 hours of sleep to get a 70%, which would be a C, all right? If you want to get a 90, right, the best grade there was on the test, it looks like, well, one person did that with 7 hours, but that's not our estimate. Our estimate is where the line crosses, right? So that's 9 hours to get a 90%, all right? If we're using this scatter plot to estimate, we're going off our line of best fit, not just a point, right? The point is what one person did. The line is an estimate of what other folks might get, okay? Obviously, you could get less sleep and still get a 90, or maybe you could get more sleep and still get a 90, okay? But our estimate is right here where the line is at, right? If we're asked to estimate, we're going to use that line of best fit, right? So then our next page, we started talking about the equation for that line of best fit. We talked about how we're using slope intercept form, right? Y equals mx plus b. That's slope intercept form of equation. All right. We call that slope intercept form, right? Because m is the slope and the b is the y-intercept, right? So we use the y-intercept where it crosses the y-axis, and the slope, right? The rate of change. So we also drew in like this slope triangle. All right, we figured out this goes from $100 up to $425. I think some classes we said $450. Some classes we said $425. It doesn't really make a difference here. Some classes we had 350 over 10. This class we had 325 over 10. That was the change, right? 425 minus 100 would be $325. And it went from 10 degrees all the way over here to 20 degrees. So it went up 10 degrees and it went up $325. We do 325 divided by 10. That makes 32.5 degrees per, I'm sorry, $32.5 per degree that the temperature increases. And we started with $100 at 10 degrees right there. All right. So that'd be our slope intercept form for that one. All right. And this is, again, is a positive, right? As temperature increases, the dollars here increase. And I think we gave some examples of what maybe this graph could tell us. We said maybe this is like ice cream sales. As temperature increases, the sales of ice cream here would increase. Maybe it's like a pool or a water park, right? As temperature increases, their sales are going to increase as well, right? More people are going to go there as it warms up, right? And then the last problem we did in class last time, here was number 1 on page, looks like 3B. So we said which scatter plot shows the relationship between x and y if x represents a student's score on a test and y represents the number of incorrect answers a student received on the same test. All right. So for that, this one doesn't make sense because there's like no correlation here, but there's certainly a correlation here. On B, we see that as the number of incorrect answers decreases, right, as this is going down, we see the test score is going up. All right, which makes sense, right? This is a negative correlation. This was the correct one here. This is B, right? Number of incorrect answers, we want that to decrease, and that will make our test score increase. All right, so this is a perfect negative correlation, right? For each problem that we now get correct, right, our test score is going to go up by that same amount, right? And we see that just consistently, all right? C doesn't make sense. That's a increasing graph. All right, our test score is not going to increase as the number of incorrect answers increases, right? The more you get wrong, the higher your score goes. That doesn't make sense. And then D shows us the test score is the same no matter what, right? Whether we miss like all the questions way up here or we miss none of the questions, we have the same test score. And that wouldn't seem very fair. All right, so that's also not correct. All right, now starting your new work, ideally you guys are kind of working ahead on these, and then just going back and checking your work with the video. If you're just writing down the answers, that's really not going to help you on the CFA. That's not really the point of this packet. The point of this is to learn what you're supposed to be doing, understand what you're supposed to be doing, so you'll be ready for the CFA, right? Which is the big part of your grade. This is 20% of your grade. The CFA is 80% of your grade. Right? So I'd much rather you learn and understand from this video than just like fill out the whole packet. That's not really the goal here today. All right. All right. So number 2, it says the scatter plot was constructed on the graph below and a line of best fit was drawn. What is the equation of this line of best fit? All right. So first of all, and the easiest thing to see here on our line of best fit, I'm going to go and zoom in some more. Easiest thing I think to see is our y-intercept, right, where that graph starts. Right, and it clearly starts here at 25 something. I don't know what that is. There's no label here, but that's at 25, right? So I can go ahead and, this one starts at 5, this one starts at 5. I can go ahead and rule out that one and that one. Those don't make sense, all right? Because I know it has to start at 25. All right, so it's either B or D. Next thing I need to know is the slope, all right? How much is increasing for every 1? So when I go from 0 to 1, how much does it go up? So this one goes from 25 up to 30 for every 1, right? Then it goes from 30 to 35. That's another up 5, right 1. It goes from 35 to 40, up 5, right 1, up 5, right 1, up 5, right 1, up 5, right 1. Every time it's going up 5, right 1. So that's D, right? This one has a slope of 1. It's not 1. You might get confused and think it's 1 because it's going up 1 line, right 1 line, up 1 line, right 1 line, up 1 line, right 1 line. But each line here that we're going up is 5. Each line that we're going right is 1, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 5, 25, 30, 35, 40, 45, 50. It's going up by 5, right? So that's D. All right, that's our line of best fit for that scatter plot. All right, go to the back of that page. How can the equation of a linear model, trend line or line of best fit? All right, so 2 different words we can call that. Be informally drawn and determined. So examples says make a scatter plot of the data on the table, draw a line of fit, line of best fit, write an equation of the line. All right, so we're gonna have to make a graph here. I'm just gonna, looks like we already have the graph kind of here. Let's start with -2, 2. So -2, and these are the x's here, and these are the y's. So we're gonna go left 2, and then up 2. -2, +3, so left 2 and up 3. -1, +2, that means left 1 and up 2. 0, 1, so 0 and then 1. 1 and then 0. 1 and then 1. Whoops, that wasn't 1, 1, that was 2, 1. Get rid of that point. 1, 1. 1, -1. 2, -1. And 2, -2. All right, so now we're going to draw a line of best fit. So that's not too bad. Let's go ahead and make our line on here. Let's see, do I have something straight I can use here? I guess I can use this notebook I have here handy nearby. And try to make sure that it's kind of here in the middle. I'm going to use a different color pen just so my line is a different color than my points. All right, so there's my line of best fit. It's pretty much there in the middle. And now we need an equation. All right, so first of all, it looks like it crosses the y-axis here, right between 0 and 1. So y equals something times x, and then that's a positive, right? So like maybe it's like +1/2, +1, somewhere in there. You could put 0.5. I'm going to use a fraction. I'm going to use 1/2. You could use 0.5. It's the same thing as 1/2, right? And then I need my slope. So how much it's going down for every 1 it goes to the right. Well, I don't see any really good lattice points here. This one's pretty close to a lattice point. What's another one? This one's pretty close to a lattice point too. Right, kind of starts there. So let's go from here all the way down to here. That's down 1, 2, 3, 4, 5, 6, 7, 8, 9 points. That's down 9 from here to here. And it's going right 1, 2, 3, 4, 5, 6, 7. Oof, that's -9 over 7x plus 1/2. That is not a fun slope or y-intercept, but that is our equation. All right. So if you had something close to that, right? I'm not asking you to have the exact same equation I did. If yours is pretty close to that, great job. Maybe yours is like -1x plus 1. Somewhere, this probably needs to be somewhere around -1. All right, it doesn't need to be negative, right? Because it's decreasing. Probably around -1. Maybe like -1.5, -3.5, something like that. Would be close as well. Something near -1. And this needs to be something probably between 0 and 1. 1 would probably be okay, but something close to there. All right. All right. Let's go on. Same thing. It says the scatter plot diagram illustrated below. plots wine consumption in liters of alcohol from wine per person per year against deaths from heart disease, right, and deaths per 100,000 people for 19 developed nations, and formally determine a linear equation that would represent a good linear model, state the type of correlation that exists. Well, this one looks like it decreases to me. If I was to try to draw a line of best fit, probably do something like that. Probably have my line kind of down here, down the middle here. All right, so this is certainly a negative relationship or a negative correlation. All right, so negative relationship, or you could use the word correlation. It uses the word correlation here, so it would probably be a good idea to use the word that they're using in the question, negative correlation. And we're also supposed to have a linear equation. It doesn't necessarily say to have a equation this time, but it's probably a good idea. Y equals, let's see, we start here at, it was like 275. That's halfway probably between 250 and 275. So it's going to be x plus 275. And let's see, this is 0. We go down 275 in, what is that, like between 7 and 8? Maybe like 7.5 somethings. Let's see what that is. I do it on my calculator here. That's 275 divided by 7.5. I get about 37, and it's decreasing, so that's about negative 37x. All right, that's from this 275, right? 275 over, it's like 7.5, all right, and it is decreasing, right? It goes down 275. All right, so that's where I get my negative 37. It's negative 36 and 2/3, negative 36.6 repeating. I'll just put negative 37x plus 275. All right, next one. Data below represents the performance on a math test and the number of hours a student studies. Say the type of correlation that exists. We can be a little quicker on this one. Just type of correlation, that's fairly easy, right? This is a positive correlation, right? Positive. And we could even say maybe strong. Maybe it's a strong positive, and we're using the word correlation here. Correlation or relationship. Either one of those words would be fine. All right, but that's pretty strong. Those points are all pretty bunched up there on my line. All right. Again, we could do an equation. I'll skip off on the equation this time. All right. Determining the equation of the line of best fit. You see LOBF there, talking about line of best fit. A description of how two variables are connected. An independent variable is the variable that is changed or controlled in a scientific experiment to test the effects on another unknown. It is often represented by this variable. A dependent variable is the variable that changes depending on the variable of the independent variable. The value of the independent variable, my fault. And then the line that best describes the relationship between two variables in a scatter plot that possesses a linear relationship. Hold on. I'm having a problem with my, where'd it go? All right. So looks like we're supposed to fill in some blanks here. A description of how two variables are connected. That is either like our correlation or relationship. We can say that's positive or negative. We're looking for the correlation here. The independent variable is our x variable. All right, I believe is what we're looking for there. The dependent variable then is our y. And then the line is our line of best fit. All right, our line of best fit. All right. General form of the linear equation that models or describes data, possesses a linear pattern. I think we're looking there for our y equals mx plus b. Slope is our m. All right, we use rise over run for that. All right, so here we have our, so this would be our run, right there. This is our rise. What's this pointing to? That's our rise, that's our run. I guess this is our independent variable here. Oh, this would be our, our y-intercept. Right, rise over run is how we find our slope. So this would be our dependent variable. Right, this is obviously the y, this is the x, right? All right, so we got all that kind of labeled there, straightened out in those boxes there. All right, so there's a little bit of notes on our graphs, which could be helpful in the future. All right, let's come over to scatter plots and line of best fit. The scatter plot shows the number of CDs in millions that were sold from 1999 to 2005. The trend continued about how many CDs were sold in 2006. All right, so we're looking for a trend line here, or a line of best fit, to figure out how many there would be in 2006. All right, so if I have my line here, it looks to me like 06 is right around 650. Is that million? Yeah, that's in millions. All right, so about 650 million. All right, and that's right here, right? This is 2006 right here. That's 05, so that's 06. All right, the table below shows the predicted annual cost for a middle-income family to raise a child from birth until adulthood. Draw a scatter plot and describe what relationship exists within the data. So the cost of raising a child born in 2003, child's age 3, 6, 9, 12, 15, those are our X's. Annual cost 10,700, 11,700, 12,600, 15,000, 16,700. So let's plot our points here. So 3 years, that's 10,700, so it's somewhere right around here. 6 years, 11,700, so we're right around here. 9's 12.6, 12.6. 12 is 15,000 exactly, so that's nice. That's right there on the lattice line. And then 15 is 16.7, so right around there. Our scatter plot and describe what relationship exists. So that's increasing, right? It's getting more and more expensive to raise the child, right? More money each year. So that is a positive correlation or relationship. They're using the word relationship this time, so I'll use the word relationship. That's a positive relationship because they're both increasing. All right. Make a scatter plot of the data in the table. Draw a line of best fit. What is the equation of the line of best fit? All right, so we have -2, +2, right around there. -2, +3. This looks very familiar. -1, +2, there. 0, 1, right there. 1, 0, right there. 1, 1, right here. 1, -1, right here. 2, -1, right here. 2, -2, and 3, -2. Draw a line of best fit. What is the equation of line of best fit? There's my line. This time here I crossed right at +1, so that's y equals something times x plus 1. And honestly, I'm going down 1 and right 1 right here. All right, and that's probably a pretty good line. Obviously, mine's not perfectly straight. Right, it'd be better if I used a ruler. I didn't, but I'm going down 1, right 1. So I'm going down 1 is my rise, right 1 is my run. That's -1 over 1 is -1. All right, so that's my slope, -1. Education, it says the table at the right gives the number of hours spent studying for a science exam and the final exam grade. Draw a scatter plot of the data and draw in the line of best fit. All right, so we go from 0 up to 5 on study hours. So here's our study hours. And I think we can just go 0, 1, 2, 3, 4, 5, 6, 7. And that's plenty because we only go up to 5. On my grade, I might need to be a little more precise here. I got to go from 60 to 90, 92, I guess, really. So if I started at 60, 65, 70, 75, 80, 85, 90, 95, that would actually work right there, wouldn't it? So I can do that. I can do 60, 65, 70, 75, 80, 85, 90, 95, and that would be 100 right there. Right. So let's go ahead and plot these. 0 hours, we get a 60%. That's right there. 1 hour is a 70%. 2 hours is 77. Right there, kind of in the middle-ish. 3 hours is 84. 4 hours is 90. Oh, there's another 3 hours, 75. And 5 hours is 92. So there's our best grade, 5 hours. Draw a scatter plot of the data and draw in the line of best fit. So our line of best fit, maybe around there or so. All right, kind of in the middle of all those points. Try to make it perfectly straight. What is the equation for line of best fit? Well, my line of best fit, my grade started maybe kind of there in the middle. Y equals something times x plus is like 62, 63, somewhere around in there would be pretty good. And then for each hour, I went from 62 to like 69, 70. So that's like plus 7. Maybe it's like 7x, 8x, somewhere around in there, right? It would be pretty good. It says predict the grade for a student who studied for 6 hours. So 6 hours right here, that's over 100, right? My line here goes over 100. So it's like 102, maybe, right? Somewhere around there. Could this line go on forever? Why or why not? No, it doesn't make sense. It doesn't even make sense to go to 102, right? Because typically a test is going to max out at 100%. Maybe there's some extra credit or something. But I'm going to say no. The test grade shouldn't go above 100%. Right? That doesn't really make sense. Right? We should stop at 100% there. Right? All right. Keep moving along. Given the data in the graph below, find the line of best fit. So which one of these could it be? If I kind of draw a line in here in the middle-ish. All right. It looks to me like I'm crossing here in the negative. So probably not this one or this one because those are both positive. All right, so probably neither one of those. And on this one here, the slope is going to be pretty easy. I don't really have to calculate it. They're all 7 over 10 or 10 over 7 for this one, which is already ruled out because it's got a positive 0.71. I know it's going to be negative 0.71 because it's crossing here below the origin. Right? So it's either positive 7/10 or negative 7/10. This line is clearly decreasing, which only leaves B then as an option. Right? Only B there is an option because it's a decreasing slope. So that first number in front of the x needs to be negative, and is a negative y-intercept, negative 0.71 here. Right. For the graph of the data points, find the equation of the linear regression line for this data. That's just talking about the line, the equation for the line of best fit. It says, note, each horizontal and vertical line represents 1 unit. All right. So that would change things if it was counting by more than 1 for our slope or y-intercept, but it says it's not. All right. So if I'm trying to put in a line, it's probably not great. Here's my x-axis, here's my y-axis. So again, this one's crossing at negative, and mine's almost at -2. All right. So this would be my best answer for that, where my line crosses the y-axis, and negative 0.589, negative a half, maybe. I don't know if that's great. Looks to me like we're going down 1, right 1, down 1. It's almost right 2 that time. That'd be 1 over 2. That would be about a half. All right, so I'm going to go with C. I think that's probably our best. That's tough. I wouldn't give you one like that on the test. Those numbers are too close together. Well, I think A and B and C are probably too close together. The other ones are pretty far off. I think A and C are pretty close. It makes that one pretty hard. For the graph of the data points, lay your ruler along the line of best fit and draw the line of best fit. Which of the following is the best approximation for the slope of the line? All right, so let's try to get, again, I wish I had one of my clear rulers for my classroom for this, but if I'm drawing my line of best fit, let's try to get it kind of here in the middle of my points, maybe right around in there. Try to get maybe like half the points kind of below it, half the points above it, and then I need to calculate my slope. So it looks to me like I'm going up. If I go up 1, I'm going right almost 2. All right. So I would say the closest one there is 1/2 or 0.5. This right here is up 1 and right about 2. All right. So that's 1, that's 2. 1 over 2 is 0.5. I think that's our best approximation for our slope. Definitely not -1. It's definitely not negative, right? It's got to be positive. All right, the function f of t equals 1.4t plus 1.9 shows cost of a hamburger with different number of toppings t. What is the slope, and what does it mean within the context of the problem? So this is a little bit of review from when we were doing functions last time. This slope here, right, is our number right here. That's our starting cost for the hamburger. So it's $1.40 is the slope. What does it mean in the context of the problem? It shows the cost of a hamburger with different number of toppings t. So that's the cost per toppings, right? So it's $1.40. That's the slope, and that's per topping. All right, so each additional topping you want to get on your hamburger, it's going to cost you $1.40. What is the y-intercept? What does it mean within the context of the problem? So that's $1.90, and that is the cost of the hamburger with how many toppings? No toppings, right? That's our starting cost. All right, so that's with no toppings. So if Jody had 4 toppings, how much did she pay? So we're solving here then for f of t, right? 4 toppings. So that's $1.40 times 4 toppings plus the $1.90. Well, calculator time, right? 1.4 times 4 plus $1.90. What is that? 1.4 times 4 is $5.60 plus $1.90. Whoops. So $7.50. So f of 4 is $7.50. Right. Another function, f of c is 25.85 plus 5.95c shows the cost of Mr. Maniscalco to go to a buffet for lunch with C of his friends. It's interesting. What is the slope? What does it mean within the context of the problem? This one might be a little confusing for some of you guys because they've got it backwards, right? They put the starting cost here and then the cost per friend or the slope here, right? So the slope here is $5.95, and that is the cost of the buffet for each friend, right? For each friend, right? That's C friends, and it's this whole thing is the cost for him to go to the buffet. So it's $5.95 per friend plus $25.85 to start with. I don't know why it's so expensive just for him. All right, the y-intercept then is the $25.85. What does it mean? Well, if he had 0 friends, right, if it's just him, that's how much he's going to pay. All right, cost of the buffet for just Mr. Let's call him Mr. M. I don't really want to write out that whole name. All right. So if he paid $49.65, how many people were accounted for on his check that day? Yikes. So we're solving for C on this one. So we're going to do the $49.65 equals the $25.85 plus the $5.95 C. All right. This is a little different. We didn't do this when we were solving our functions. We were plugging in for for C. But this is not that. This is asking how much. This is telling us how much he paid, the total cost. And we're supposed to solve for C, how many friends he had. Right. So first thing we're going to do is subtract the 2585 from that 4965. So again, time to go back to the calculator. 4965 minus the 2585 leaves us with 2380. And that's how much he's got to pay for his friends. All right. $5.95 per friend. All right. So all we've got to do then is divide that 2380 by the $5.95 per friend. And that will tell us he had 4 friends. All right. 4 friends. All right. And we're done with the interpreting slope and y-intercept. All right. All right. Active dentist in the U.S. making sense of data. All right. So year 0, 5, 10, 15, 20, 25, 30, and the number of dentists. All right. So we see the number of dentists are decreasing. First 5 years goes down by 2. The next 5 years goes down by 3. The next 5 years goes down by 2. The next 5 years goes down by 3. The next 5 years goes down by 8. And then that final 5 years goes down by 14. Right? Is there any constant rate of change within this data? Right, so that is not a constant rate of change, right? That's no, because it's changing by different amounts, right? Each 5 years. It says pick any 2 points and calculate the slope. All right. We can do this. This is what, 2, and this is the y. So this would be what, down 2, and this would be up 5. So this would be -2/5. That'd be our slope there. What does slope mean in the context of the situation? It's the decrease in dentists per year, right? We're losing 2/5 of a dentist per year. Doesn't really make sense when you think of it that way, but we lost 2 in 5 years, so that's what that means. It says calculate the line of best fit. Use mathematics to explain how you determined your answer. Use words, symbols, or both in your explanation. All right. Well, I guess let's get after it. How many lines we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 lines. And we got to get up to 30 years. That's not very nice. I guess we can count by 2s. I guess really just 5s makes sense though, doesn't it? Since we're going by 5s there. So let's just do 0, 5, 10, 15, 20, 25, 30. It's kind of a silly looking graph. We're not going to use very much of it. All right. And then the money is going to be much harder. All right. Or sorry, not the money. The number of dentists is going to be much harder because we got to get that's a range of numbers, 154 to 121. That's a range of 33 that we've got to span. All right. And we've got what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 lines. So 12 lines for a range of 33. So I got to count by 3s, right? Because 12 times 3 is 36. So that's my best. So if I start at 154 at the very top, and I'll just decrease by 3 every time. So 151, 148, 145, 142, 139, 136, 133, 130, 127, 124, 121, and then I'm going to say, skipping some, right? I'm skipping from like 0 all the way up to 121 there. All right, and we're going to start at 0 and 154, right? Our first year there is year 0. We had 154 dentists. Year 5, we had 152, so that's right in here. Year 10 was 149, right around there. 15 was 147, pretty close there. 20 and 144, 25 and 136, oh, right on the line, that's good. And then 30 and 121, big drop right there, right? Thanks. All right, so if I want to try to get all these points, right, I'll leave it right here in case you want to pause it and get a better snapshot there. All these points are on our scatter plot here. I don't know. Do we want to say that's an outlier and just not include it in our line? Because I think our line is going to look much better if we don't. If we just do something like that, our line's going to look better. If we try to include this point and have it close to the line, that line's it's gonna be pretty far away from a lot of these points. All right. And identify the y-intercept. So my y-intercept was what, about 152 or so. All right. And then what does the y-intercept mean in the context? So started with that many dentists, 152 dentists, even though we didn't, right? But that's what our line of best fit says, even though we actually started with 154. All right, so our line of best fit's kind of deceptive right there. All right, review for lesson quiz on bivariate data. That's a problem that we did. All right, so if you want to go back and do that one again, you can. But it was on that very first page that we did. Right, we graphed those for 8th grade students. All right, so you can go back and do that one again if you'd like. Joe the plumber charged $25 per hour plus a visitation fee of $50 using extra hours. Y for total cost. State an equation for this. So $25 per hour is 25x, and $50 per the visitation fee. That's that one-time fee. All right, state the value of the slope. So the slope is our 25. The y-intercept is the 50. All right. What does the slope represent? It's the charge per hour. What does the y-intercept represent? It's the cost per visit, right? That's like how much it costs just to have the guy come out to your house there, right? So that's number 3. I guess we're going out of order a little bit here. There's number 2 down here. It says state whether the data may possess positive, negative, or no correlation. So test scores and hours of studying. We would expect your test score to go up the more hours of study you have. So this would be positive. Balance of bank account and the number of trips to the mall. Well, that should be negative, right? Your bank account should probably go down the more you go to the mall. Makes sense. And the eye color and salary, we would say that's no correlation, right? It doesn't matter what color your eyes are, but for how much money you make, right? Some businesses maybe, if you're a model, right, maybe they prefer a certain color of eye. But overall, right, we would say eye color has no correlation with salary, right? That wouldn't make any sense. All right, last page, we're almost done. Table compares the number of hours spent in the mall and the amount of money spent. Draw a scatter plot to show how many hours shopping relates to amount of money spent. All right, so hours in the mall, we go up to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So I could almost even go by like half hours if I wanted to. I don't know that really makes sense to do that though. But I guess, yeah, sure, let's do it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we'll skip a line, and that really just helps us because those lines are so small, so close together. It makes it hard. Dollars spent, we got to get up to 100. How many lines we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we got to count by probably tens there to get all the way up to 100. Better write small if we're going to fit all these in there. I might just skip some here. 30, 50, 70, 90, 110. So I'm just counting the odd numbers there, right? I guess really all those are even numbers, but at least the tens digit is an odd number. 1, 3, 5, 7, 9, 110. All right, for 10, 30, 50, 70, 90, 110. All right, and let's plot those points. So 1 hour is $10. 2 hours is 35. 3 hours is 20. So I've done 1, 2, 3. Oh, there's another 2. 2 hours and $100. Person just got in and spent it all. 3 hours and 60. There. 5 hours and 50. 6 hours and 70. Since I'm going out of order here, I'm kind of checking them off as I go. 7 hours and only $18. They were just hanging out, huh? $8 and 8 hours and $25. 8 hours and $15. 9 hours and $24. And 10 hours and $40. Right there. I don't know. I'm not sure I see a correlation. Some of those people who were there the longest didn't really spend much money. Some of the people there that were there for only a couple hours spent a lot of money. I'm not sure I would say there's any kind of correlation. Describe and identify the association. Hey, association is another word for like correlation or relationship. Okay, so they've thrown a third word at us now for that. I would say none. All right, the points, I would say they don't line up. All right, draw and state the equation of the line of best fit. Again, I'm not going to have one, right? Because I don't think there's a correlation. All right, so I would say not applicable. All right, NA doesn't exist. Uses to predict the money spent if a person spends 4 hours shopping. I mean, I guess if you want to say like 4 hours, it's probably around in here somewhere. But again, I don't know that we have a line, like a specific amount there we could really even estimate. All right, back here, right, these points tend to line up a little bit. And then these people who were here for a long time, it seems like maybe they were working there, right? So maybe we have shoppers here and we have people that worked there here. And maybe that's two separate lines, right, for how much money they spent. Right, another line here for how much money they spent. So maybe if you were just visiting to shop, maybe you spent about, I don't know, 50, 60 bucks. But I don't like it. I don't think that's a good one there for our line of best fit. So I wouldn't worry about that bottom part there either. All right. Last problem. It says the table below shows the prices during a 40-year period for a first class postage stamp. So the years go from 1971 all the way to 2013. That's a wide range. 40 years. Yeah. That's not quite 40 years, though, is it? It's 30 and 12. That's 42 years. Complete a scatter plot of the data on the grid to the right. All right. Time, I like to always have as my X. And what we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines. And we got 32 years. Well, if we only had, no, it says 40 years. Oh yeah, 42 years. I was right. So I got to count by at least fours here. That's only going to get me the 40 years they're talking about. It's not going to get me to 2013, is it? I could go by fives, I guess. So we'll start at 1970. I'm going to turn it this way so I can write my years out without taking up quite as much space. So 1970. And what if I just put, like, these are all 19, right? So 75, 80, 85, 90, 95. Oh, here's 2000. So then 05, 2010, and 2015. All right. And then I need the prices. Prices are a little easier. I got 10 lines again, it looks like. My range of prices here is what? 38 cents in range. If I start at 0 here, go all the way up to maybe up to 50 would be good. I got to count by fives there as well. All right, kind of on years by fives. And I'm going to count by fives here on the cents as well. So do 5 cents, 10 cents, 15, 20, 25, 30, 35, 40, 45, and 50 cents. All right, so 1971, right around here we had 8 cents. 75, we had 10 cents. 1981, we had 20 cents. Pretty big jump there. 85, all right, like that. That's 22 cents. 1991, 29 cents. 1995, I like that, it's on the line, 32 cents. 2001, we have 34 cents. 2010, another one on the line, I like that, 44 cents. And 2013, we have 46 cents. All right, hey, that's a pretty good scatter plot. All right, we can definitely see a trend there happening. It's asking for the trend line. Let's see if we can draw that on there. I'll use a notebook again and try to make it a little straighter. Smear my ink too much. Let's see. Be easier if I had a clear ruler. Would have been better. But that's pretty good. Where I got 1, 2, 3, 4 points above it. 1, 2, 3, kind of 4 points below it. A couple of them are kind of on it. But like maybe 4 above and 3 below. So that's a pretty good line. All right, draw a chin. So complete the scatter plot. Check. That's done. Draw a trend line or line of best fit. The best fits the data. Done. Describe the association. Explain what it means. All right, so this is positive. We could even say strong positive, right? Because those points are pretty much right around that line. So strong positive, what does it mean? It means as time increases, the cost also increases, right? The cost of the stamp increases as the years increase or as time goes on. What does the slope represent? All right, well, what is the slope? Here's a good point we could use to find slope. Here's another one. So it's going up about 5 cents for every 5 years, about 1 cent per year. All right, this is up 5, right? 5 cents from 20 to 25, and that's in 5 years from 85 to 90. All right, so that's about 5 cents in about 5 years. 5 over 5 is equal to 1. 5 divided by 5 is 1. So that's about 1 cent per year. And that's the increase in the cost of a stamp each year. It says using your equation, what would the price of a stamp be in 2005? Does it ever actually ask for the equation? It never actually asked for the equation, but it says using your equation, so we better have one, I guess. Y equals, well, that was just 1x, right? Or x plus, I don't know, what do we start with here? At this year, I guess really that's like 1965 that we started at. Was that maybe like 2 cents per stamp plus 2? What would the price of a stamp be in 2005? Oof, it's a long ways away. So we started in 1965. So we got to use that as well. 1965. So we're doing 2005 minus 1965. That's 40 years. So I need to put in a 40 right here. All right. So y equals 40 plus 2. Y is 42. That would be 42 cents, right, for that stamp. Let's see if that's about right. 2005. Let's go back to our data. 2005 would be right here in the middle, and it'd be 42, which is in the middle. It's closer to 44, but it's in the middle-ish. That's not a terrible estimate. That's a pretty decent line we have there. Then it says find the equation of the trend line using 1985 and 22, and 2010 and 44. All right. So our rise, right, the up and down amount here is the cost. So it went from 22 cents to 44 cents. So our rise is 22 cents. And the amount of years here that takes, well, that's 15 and 10 more. That makes 25 years. Hey, that's pretty close. I don't think there's actually a common anything there to go into that. I guess we could divide it and turn it into like a fraction if we wanted to. That's not really going to be more accurate. It's just going to be a different version of that number. 22 divided by 25. gives us 0.88. All right, 0.88. That'd be 0.88 cents per year is the increase in the cost of a stamp per year. All right, so that's pretty close to the 1 cent per year that we said. All right, we weren't far off in our estimate and our trend line. All right. Okay, so that's it for scatter plots. If you finished all this, I think you're probably ready for the CFA. So we'll have that CFA coming up, and we'll have the retake. If you have any questions, feel free to message me on Google Classroom. Be happy to help and try to get this finished today in class if you can. Hopefully, if you've gotten to this part of the video, you're probably finishing. All right, thanks guys. Have a good day.